All right, so in the previous week, we talked about solving trusses by looking at the individual joints and drawing a free body diagram about each joint, which is what I just talked about, right? That method, where we looked at each joint individually, is called the method of joints. So the method of joints is simply the method where you will look at each joint individually, draw a free body diagram at each joint in order to find the forces. Now, there's another thing that we said last week. In addition to looking at each joint individually, you can actually look at your structure as a whole. You can look at that combination of trusses as one body. And you can do that to find the reactions, right? So today we're going to look at one method that kind of combines the big picture, little picture approaches. And that's going to be called the method of sections. But before we start talking about this method of sections, let me first explain the philosophy behind the method of sections. So what makes a system static?
All forces equal 0.
Exactly. All forces equal 0. Now, even though that statement, it seems like the sum of forces, there we go. The sum of forces equals 0. So even though that statement looks like a very generic, very easy statement, there's a lot of power to that statement, because if I were to say this is your system, and this is a static system, you said the sum of forces equals 0, right? Which means that if I take all the forces acting on the system, weight, normal force, atmospheric pressure, maybe some tension, some compression, some shear force, and add them all up, it's going to be 0. But then what happens if I only take a section of this system? You see, in order for all your forces equaling 0, all the sum of forces equaling 0 in your system, the sum of forces actually have to equal 0 at every point in that system, not just at the system as a whole, but also at individual points in the system. So, for example, look at me. I'm standing, and let's say that I'm static. I'm not moving. Of course, you know that I'm experiencing a gravitational force, and I'm experiencing a normal force from the floor. Let's neglect atmospheric pressure, right? So based on this, normal force equals gravitational force, and I'm static, right? But what about, let's say we zoom in. What about my heart? I know that's not what hearts look like, but what about my heart? If I'm static, right, and I look at my heart as a static system, then in order for this to apply to me, the system, right, in order for sum of forces equals 0 to apply to me, it also has to apply to my heart. Now, of course, we're going to neglect any movement from pumping and all that stuff, but just looking at the heart as a static system, if my sum of forces equals 0 here, they have to equal 0 here. But then how is that? Well, let's see. The heart is only a portion of my body, which means that the heart will only exert a portion of my weight, right? So it's just the weight of the heart. So how can this heart remain static? If there's only one force, it should just sink all the way down to my leg, right? So how can this heart remain static?
The rest of your body is holding good.
Exactly. The rest of my body is keeping it in place, okay? Now that doesn't just apply to me, to my body, it applies to any system that you think is static. If a system is static, it will be static at every part of that system. And if you think, well, we have a bar, let's say we have a bar fixed to a wall, and we apply a force, and obviously, you know, the wall has these two reactions that keep it in place. We have the weight. We say that this is static. The system has to be static everywhere in the system. Everywhere, at any point. So if I were to just focus on this portion of the bar, this bar has to be static just like the rest of the entire thing. And how does that happen? Well, this little portion is experiencing this force, is experiencing its own little weight. So what's keeping this portion of the bar in place?
So our dotted line acts as our wall.
Sorry?
So the dotted line we have acts as our wall.
So
it's like a mounted.
Exactly, right? This part of the bar acts as a wall that provides the necessary reactions for this bar to remain static. We're going to look more into that in next chapter, which is internal forces, but I wanted you to get the philosophy behind it at least, that if a system is static, then every point in that system is static. And we're going to use that philosophy to apply this method of sections. Now, I personally would prefer to teach internal forces first, but I also respect the way this book is structured, because it is structured very well. So we are going to study the method of sections, but keep that in mind. Keep in mind that if a system is static, then every point in that system has to be static. So the method of sections consists of taking any truss system. Let's say we're looking at this system of trusses, and I'm just going to draw them this way. So you have these trusses connected by these joints, and you could, right, calculate the tensions or compressions in each joint, right? This won't, I don't want to write that. It doesn't matter whether it's tension or compression, but you can calculate them, okay? Now, maybe I'll draw one more. You could calculate them, okay? Now, what happens if you have a large system? So something with like 15, 20 different trusses. You're going to have a lot of joints, right? Many trusses, many joints. So sometimes, in order to find reactions in a system, it may not be necessary to calculate the entire system. For example, if you're looking at this system and experiences of force here, if you're looking at this system, okay, and I were to ask you perhaps to calculate forces, let's say in these 3 bars, then it's not really necessary to calculate the forces in every single joint. If you're using the method of joints, then you have to. But we're going to introduce a new method that's going to help simplify our calculations so that we can reduce or break down our system only into the part that we need to analyze. And that's the method of sections. So the method of sections consists of you cutting a section in your system, and then only analyzing one of the sides of that section. Now, what we're going to learn today is that as long as we understand how to cut our system and how to analyze our system, then we don't really need to solve the whole thing, right? So if we only want to solve 1 or 2 joints, we can cut our system near those joints and only solve for those 2 joints. So let's go ahead and explain how that works with an example, because it is a bit of a, I mean, I'm not a big fan of explaining trusses with theory. So we're going to do a quick example of the method of sections. Let me see if I can find a good one in my book. There we go. Okay. So let's look at example 6.5. And don't worry, we're going to explain all this theory as we solve the example. It's just like how we solved the method of joints, right? Going through the theory. So let's say we have this truss system. Remember, don't take my drawings as the best because they're not. Here's some calculators. That's good. Pull out your calculators because you will need to use them. We're almost there. We're almost there. Okay, we have this truss system. This truss system is supported on a hinge and on a roller. Let's give some dimensions. Let's say that each horizontal truss is 4 meters in length. And let's say that this vertical truss is 3 meters in length, obviously not drawn to scale. I'm going to give these joints some names: A, B, C, D, E, and G. I guess no F so we don't confuse it with the force vector. And I'm going to have some forces acting on this system. We're going to have a 1200 Newton force acting on joint C. And we're going to have a 400 Newton force acting on joint E. Now, just by looking at this system, and based on what we learned last week, if I were to ask you to solve this system, in other words, to solve or find every force in every truss, whether it's tension or compression and the magnitude, could you solve it? Given this information? Yeah, we could, right? And the way we would solve it using the method of joints is by drawing free body diagrams about every joint. So we'd have a free body diagram for A, a free body diagram for B, a free body diagram for C, D, E, and G. Let's do a quick review. We're not going to solve it using the method of joints, but let's do just a quick review. At A, how many forces can you identify just at A? Just 2?
3, 2, 7 moments.
Just 3? 4? Okay, what are those forces, Lorenzo?
There's the X reaction force.
Mm-hmm.
There's the Y reaction force. Then there's force AG and force AB.
Exactly, right. A hinge gives you 2 reaction forces, AX, AY. But then you also have to consider the tension and compression of AG and AB. Is that correct? Does that make sense? Okay. So now let's try it. At B, how many forces can you identify? 3, right? What are those 3?
BG,
Mm-hmm.
BA,
Mm-hmm.
BC.
Now, what did we learn about these T-shaped members? What do you think?
The vertical force would be 0.
Exactly, right?
And the 2 on the side would be equal and opposite.
Exactly, right? So we have these 2 bars, these 2 trusses have to be equal. And then this force has to be 0. At C, how many forces can you identify? 1, 2, 3, 4, 5, right? You have the 1200 Newton force and the tension from each of the 4 bars that are connected to it. What about D? 3? Okay, so a reaction force from the roller and then 2 tension or compression forces from the trusses. What about E? 4. And what about G? 4, but we already know that B would be 0. BG would be 0, okay? Good. So as long as we understand how to identify those forces, we can apply the method of joints. Now what we're going to do today is, instead of solving for every single one of those trusses, let's find the force in GE, GC, and BC. In other words, let's say that out of all of these trusses, we would like to find the force. We would like to find the force on your member GE, GC, and BC. Okay? If you were to use the method of joints, you would have to consider this joint, this joint, this joint, and this joint at least, right? In order to find these 3 forces. And maybe you even have to find this joint and this joint as well. Which means that you would have 1, 2, 3, 4, 5, 6 equations. Well, X and Y, so 12 equations to solve. And you'll probably have around 12 unknowns. 12 equations, 12 unknowns, just for 3 values seems like a little bit too much work. And that's what the method of section, that's where the method of sections comes in. When you have 12 equations to solve, but really you only care about 3 of these unknowns, what we can do is we can simplify this system, okay, by cutting it and making it easier for us to manage. So if we were to draw a free body diagram of the system as a whole, you have your system and you would include all the forces acting on it just like I drew. So as a whole, the system, not each individual truss, but the system as a whole, the structure as a whole experiences this 1200 Newton force, this 400 Newton force, in addition to my Y reaction in the roller and my X and Y reaction in the hinge. Does that make sense so far? Okay. Okay, so we draw this system as a whole. We have all of our forces identified, and here's where the method of sections comes in. The method of sections consists of cutting your structure into a smaller structure. Now the question is, where do you cut it? You see, you're going to take your structure and you are going to cut it along the lines of the members that you want to solve. In other words, if I want to find GE, GC, and BC, I will have to cut my system along GE, GE, GC, and BC. Okay? Now there's some rules to this cutting. When you cut your system, you have to make sure that it is completely cut. In other words, that once you perform your cut, your two systems can become separated from each other fully. Now what that means is that I can't cut GE and GC and stop there, because you still have one bar that's connecting the two sides, right? So when you make your cut, you need to make sure that you cut through the entire system so that you can separate it completely. That's one rule. The other rule is that you cannot cut through the same bar twice, right? I can't cut through GE, GC, and then all the way back to GE. That doesn't help me at all, okay? So cut through each truss once, and make sure that your system is fully separated, that when you cut it, your system is fully separated. And notice that that's what we have here. We have cut this system so that everything on the left can be its own thing, everything on the right can be its own thing, and then nothing connects them anymore once we make the cut. But now the question is, what happens with that cut? So when you make your cut, you're going to choose one of these two sides to work with, whichever side is easiest for you. I'm going to choose the left side, and you'll see what that looks like. When you make your cut, what I'm essentially doing, did everybody write this down? Okay, so when you make your cut, what essentially you're doing is you are getting rid of everything to the right side of your cut, or the left side if you want to solve for the right side, okay? So in this case, I made my cut. I erased everything that I didn't care about. But then what happens? A lot of these forces disappeared, right? So how do we make up for those forces? We're going to make up for those forces by considering tensions and or compressions in these trusses. In other words, once you make your cut through your trusses, you need to consider that each truss will have a tension or compression associated with it. Okay? So what this gives me is a force from B to C, a force from G to C or C to G, and a force from E to G. I just write these in alphabetical order, but essentially it's B, C, and then node E. Now, if this system is truly balanced, this system is truly static, the sum of forces equals 0, that means that sum of forces equals 0 has to apply to this section of the system. Because if it applies to the system as a whole, it has to apply to every portion of that system, including this section. And that's where the whole philosophy of sectioning comes into play. So now what do I end up with? I end up with a slightly easier system that I can now solve without needing to worry about the 3 trusses and roller reaction force that I left on the other side. Okay? So once we do that, right, the question is, well, how do we solve the system? We mentioned that there were some forces acting here, right? Yes, go ahead.
Are we able to cut it multiple times but not through the same bars, such as like cutting along AG and AP?
So doing another cut?
Is that, yeah. Are we allowed to do that? Or?
You can, but the problem with doing it now is that you don't have any external force to account for your forces. So you can only do, you can do it, but it can only help you solve a problem if you have external forces already acting on it. Okay? So in this case, we want to make sure that we leave these two external forces that are, so we can balance them out with these forces.
Would help us in this case.
Yes, in this case, in this particular case, it won't help us. If you had these two forces, then you could just cut it into an even simpler system and then solve. Yeah. So we have this. Of course, we cannot forget about our reaction forces. But our reaction forces, I think at this point, are pretty easy to find, right? Because we had one reaction force dy, we had one reaction force ay, and one reaction force in the x direction ax. Looking back at it, I think I should have solved the reaction forces before erasing all that, but I did want to make a point. But now I kind of feel lazy and I don't want to draw it all back again. So just let's pretend that this drawing is as good as the one that I did earlier. We had a force, and we had a force. Can anybody remind me these values?
400.
Just 400? And 1200? Okay. So with this system as a whole, we can find these reactions. And let's go ahead and find these AX and AY reactions before we move on. Let's start with the easy one. What's the easiest reaction to find here between these two? AX, right? Okay. So we take our sum of forces in the x direction equals 0. And in the x direction, we have a force of 400 newtons minus a force of AX, and all this equals 0, which means that AX equals how much? 400. There we go. 400 newtons, right? We already drew it negative. Good. And of course, we have to find AY, but we know that AY, right, depends on dy. But it's okay. We can find that reaction with relative ease, right? So we can find AY by taking my sum of forces along point D and noting that the sum of forces at point D, sum of moments around point D equals 0. So what forces do I have? I have a force of 1200 newtons acting at this distance, which if I remember correctly was 4 meters. Is that correct? Okay, so 1200 newtons at 4 meters. Is this a positive moment or negative moment? Positive, because it'll be a counterclockwise rotation. Good. I have a force of 400 newtons acting at a distance, if I remember correctly, of 3 meters in the vertical, right? And is that a positive moment or negative moment? Good. Finally, I have a force AY, reaction force AY, acting at a distance of 4, 8, 12 meters. And is that a positive moment or negative moment? Negative. And all this equals 0, which tells me that AY will equal 1200 times 4 minus 400 times 3 divided by 12. And can anybody give me that number? $300 units? Newtons, that's correct. Good. So we found our reactions at the hinges. When you're cutting your section, remember, if you have any reactions, you want to solve for them first. Okay? Don't do like me. Don't cut it and then realize that you got to draw it out again. So when you cut your system, solve for those reactions first so that you can use these reactions in order to find these forces. And now my question is, now that I've cut my system, I have my 3 unknowns and I have my 2 reactions, how can I solve this system? Do I go back to the method of joints and go from here to here? That wouldn't be the case. How can I solve this system now? Now that I've cut everything, I've reduced it into my simplified system. Just as a rigid body, that's correct. So we cut our system into different sections, and we can solve each section as a rigid body, as long as we have some external force acting on it. It can be a reaction force, it can be some impact force, it can be a body force. So as long as we have an external force that we know acting on it, we can solve this as a rigid body. So we take this truss, and it essentially becomes a rigid body, or at least we treat it as a rigid body. I'm not even going to try to draw it again. Let's say we have the free body diagram here with all the forces. If I want to solve this as a rigid body, I need to apply the equations of equilibrium. Sum of forces in the x direction equals 0. Sum of forces in the y direction equals 0. Sum of moments about any point equals 0. What do you think? There is one of these three that can actually be applied and give me at least an answer without having to go back and forth between equations. What do you think that is? It cannot be forces in the x direction because we have 1, 2, 3 unknowns. So how else can we start solving this system? Forces in the y direction? Okay. Okay. So let's take our sum of forces in the y direction. I get that sum of forces in the y direction equals 0. And in that y direction, I get which forces? Which forces can you see just in this section? Which forces can you see in the y direction?
AY and then F, C, G, Y.
And what is FCGY? First off, is that going to be positive or negative?
Negative.
Negative, right? And what's the component of FCG?
So it'll be F, C, G.
Remember, we got, for each of these beams, we got 4 in the horizontal, 3 in the vertical meters.
So it's a 3, 4, 5 triangle.
Yep. So in the y direction, what's that slope? What do you think, Will? It's okay. We're looking at the y component of this bar, FCG. Now we don't know the angle, but it's okay. We are told that in the horizontal, this has a 4 meter displacement. In the vertical, it has a 3 meter displacement. How can we find that slope that allows us to find the y component? Maybe it helps if I draw the triangle. FCG, right? We have a horizontal component of 4, a vertical component of 3. What's this length? 5. Good. And remember that my force vector is going to be in the same direction. So it's going to be a similar triangle. So we have FCG. Then we have the y component of FCG. And how can I relate, or how can I relate the proportions of this triangle to the proportions of this vector? Exactly, right? FCG times 3 over 5, right? We take the slope. We're looking for the vertical component. So we take the vertical component of this triangle over the hypotenuse. Remember, sine is opposite over hypotenuse. So this 3 over 5 is just sine of this angle. So you don't need to know the angle to find the sine. You know that's already 3 over 5, okay? So we get that AY minus FCG times 3 over 5 equals 0. We know that AY is 300, therefore FCG should be equal to 300 newtons times 5 over 3. And how much is that? 500 what? Positive?
Yes.
Good. What does that positive mean? It means that this direction was assumed correctly. That means that FCG is a tension force, 500 newtons in tension. Do you see how this works? We cut this system up and we can treat it as a rigid body. Yeah.
I'll admit, I watched the video, but I'm still a little confused on when you say we assumed it correctly. Because
Yeah, let's look into
how
that.
are you evaluating?
So, because you have a truss, which is a bar, a rigid bar, this bar does not experience any bending because it's a rigid body. Okay, it doesn't experience any shear, at least not externally. So there's only 2 forces that this bar can really experience: tension and compression. If we're looking at it in the context of the joint, just the actual connection of the bar, if the bar is in tension, then the joint feels pulling, right? So you take your force to be pointing outside of the bar, right? From the bar outside of your system. In this case, I drew my force as if it were pointing outside of my system, right?
So when we're making those sections, and we're assuming that it's tension, if we had gotten a negative answer, it would still be tension, and we would just know we assumed the direction wrong, right?
Well, if we assume the direction wrong, then it's not tension, it's compression, right? So
if we got a negative answer there, that wouldn't be compression.
exactly, right? So the convention is that we set positive values as tension, right?
Okay.
And negative values as compression. So remember we said that if we get a positive value, that means we assume the direction correctly. And if we get a negative value, that means we assume the direction incorrectly. So the idea is we're always going to assume tension so that if our assumption was correct, we'll get a positive value, which just so happens to line up with our convention of tension is positive. If we assume incorrectly, we'll get a negative value, which just so happens to be the convention that we use for compression. Okay? All right, no problem. Okay. Can we finish solving this system? Yeah.
The only thing I was gonna ask, sorry,
That's okay.
when you said the slope, when we were looking for the slope,
Mm-hmm.
why wouldn't it, like, that's the only part I think, why isn't it 3/4 if we're looking for the slope?
Well, this is my angle, right?
Yeah.
Okay. This is your hypotenuse.
Okay.
This is your opposite. This is your adjacent side to the angle, right? Okay. So we use the law called SOHCAHTOA, right?
Yeah.
Now SOHCAHTOA, what that means is that the sine of the angle is equal to the opposite side over the hypotenuse.
Yeah, I got that. I was just
Yeah.
confused because I was thinking slope. It's like I was using like the rise over run.
Okay. No, we call this slope, but it's really just a sine of the angle.
Okay.
Okay? So this is the same thing as me saying, well, this is the same thing as me saying FCG times sine of alpha or theta, whatever you want to call it. Because sine of theta is 3/5.
Okay.
Okay? And of course, if it were cosine of theta, what would you use?
The 4.
Yeah, 4/5, right? Good. All right. How do we solve these remaining forces? Notice that it's not that complicated. It's just, it takes a little bit of practice to know where to make your cut. But let's just go ahead and finish solving it. Riley, what do you think? What's next?
Well, we need FEC and FEG, which we can do with the A of X. So sum of forces and extra, I guess.
See, I agree with you, except that that's going to give us two unknowns. Perhaps there's one way where we can use an equation and not have two unknowns, just solve for something directly. We want to avoid the whole back and forth, right? That's why we're doing this cut, to avoid the back and forth between equations. What do you think? Lorenzo, any ideas?
Would we do the sum of moments?
Where?
Point A.
Okay. Point A? All right. So if we were to find the sum of moments about point A, we know that those have to equal 0. What forces are causing rotation about point A? Of course, FBC doesn't count because it passes, the line of action passes through the point. AX and AY don't count because their lines of action also pass through the point. So what forces do I have to consider in order to find the moment about point A?
CG and EG.
FCG and FEG, is that what you're saying? Okay. So we get FEG at a distance of what from A? The line of action, remember, 3. Okay. Is that a positive or negative moment?
Negative.
Okay. But here I have a problem, Hunter. If I choose FCG, well, first I need to figure out what this distance is. Oh, I think I can figure it out. It's not going to be something that complicated. Okay? So what's the distance? The distance between A and this line of action of point FCG. Not unless there's a 90-degree angle between these two bars, and there isn't. I know that you can solve it. I know that it's going to take a while. Perhaps there might be an easier way that doesn't involve us having to find that force. I'm going to give Lorenzo some help. So I'm not saying that you chose incorrectly. I'm just saying that this actually gives us a little bit of extra work. I mean, we could split this up into components, right, X and Y, but the problem is, if you split this up into components, then you need to be very careful about where exactly you're making the cut. Because wherever you move this cut, it's actually going to affect your distances. And we don't want to deal with that, okay? Remember, the whole point of this procedure is not because you have to do it that way. It's just because it makes it simpler for us. And if it makes it simpler for us, I would always try to pick equations that I can just solve without having to go back to additional calculations. So Lorenzo, here's a suggestion. Sum of moments equals 0 at any point. Now, that doesn't mean that it has to be a point in my body. What if I choose, right, point C as my point? Sum of forces equals 0. Doesn't matter where you take that point. It doesn't have to be in your body. It can be any point out of your body. So what I'm going to do is I'm going to take my sum of moments, about point C. Now, if you're not sure what I'm doing, all I'm doing is picking a random, not really random, I'm just picking any point that doesn't necessarily have to be in my system and applying the equations of equilibrium. They have to apply. Yeah?
Could we also do it around G, because that would eliminate
Yep.
like FC?
Yep. And let's do it both ways. Let's do a C so we can find FEG, and let's do about G so we can find FBC, right? So let's do it both ways. So we get moments around about C. And let's start with C because I already drew it on the board, okay? Notice that this force cancels out, no moment. This force cancels out, no moment. This X force cancels out, no moment. So what forces do I have causing rotation about point C? Okay, so I have AY multiplied by the distance between A and C is 8 meters. Okay? Is that a positive moment or a negative moment? Negative, okay? And then I have a force, EG, multiplied by what distance? 3. Is that a positive moment or a negative moment? Just based on our assumption. Negative. This tells me that FEG equals negative AY, which was 300 newtons, times 8 meters, divided by 3 meters. And I'm assuming that's 800 newtons, right? Or no? But I have a negative sign. What does that negative sign tell me? Exactly. The negative sign just tells me that FEG is 800 newtons in compression, which means that I assumed this direction incorrectly. But it's okay. That's all it means. Two ways you can handle this. You can leave your arrow the way it is and just write this as a negative value, or you can change the direction of your arrow and write it as a positive value. But be careful, whatever you do, you have to be consistent so that it doesn't mess up your other calculations. And now let's do what Hunter said. Let's find the moment about point G. Notice that these two forces are going to cancel out on the moment, so we don't have to consider them. So what forces do I have about point G causing a rotation? Will? Point G.
Point G.
Yeah. What's
AX.
making that rotate? Okay, we have AX. And we have AX multiplied by that distance of, what's the distance between G and the line of action of X?
4 meters.
3 meters.
Or 3 meters.
There we
I
go.
was looking at it in the moment.
There we go. Okay, 3 meters. Is that a positive or negative moment?
Negative.
Negative, that's correct. Clockwise rotation, negative moment. What else, Will? I'm going to let you finish this problem. So what else?
Or FEG.
FEG. What's the distance between FEG and G?
Yeah.
0, right? No moment. So what else?
FBC.
FBC, okay, that's good. And what distance?
3 meters.
Positive or negative moment?
That is a positive.
Okay. I think I'm missing one more, right? What am I missing? Hunter, help him out.
So we have AY.
AY, right? 4 meter distance, positive or negative? And all this equals 0. This gives me a force BC equal to AX, which is 400 newtons, times 3 meters, plus AY, which is 300 newtons, times 4 meters. And all of this divided by 3 meters. So how much is that? 2,400 Newton meters divided by 3 meters. Is that 800 newtons? Was that a positive number? Okay, so we assumed this direction correctly, 800 newtons in tension. And look at that. We did a much simpler problem in class on Monday. Our truss on Monday looked like this. And it took us the entire class time to solve it. Here, because we're using the method of sections, and we know that we only need 3 of these elements, we can solve it a lot faster if we break it down into sections. Now, of course, it takes practice, right? It takes practice for you to identify how to make the cut correctly, for you to identify which are the best or the easiest equations to use. Remember, the whole point of sections, of method of sections, is to simplify your calculations, to make you work less. And you always want to think that when you're solving your equations. Whenever you pick a point to find your moments, you think, is this going to make me work less or not? Because if it's not going to make you work less, then you shouldn't do it, because the whole point of sections, right, is to make you work less. My advice is to always pick points where you can cancel out as many forces as possible for your moments.
So if we were to have to find like the tension or compression in all of our like beams, would it be easier just to do it with method of joints?
If you have to find every single one, yes. The method of section is just to simplify your calculations so you don't have to calculate every single one. But if you have to do it anyway, just use method of joints. And you will still be able to solve it, and you'll get the same numbers. Any questions?
So from the other side, we would also get like compression, and tension, right?
If we were to do our section on our right side section, no, we'd still, yeah, compression. No, we'd get compression, tension, and tension. It will be the same.
So like point C, it's pulling, so wouldn't that be compression then?
No, when you cut it on the other side, right? If you cut your sections on the other side like this, your forces will be compression, tension, and tension. So remember Newton's third law of motion. For every action, there's an equal and opposite reaction, right? If this is experiencing compression, this has to experience compression as well. And because we're cutting it on the other side, the force will move towards the other side, okay? Because these are the forces that are eventually going to end up at your joints, right? So at this joint, because this bar is feeling compression, this joint will feel a force coming into this direction, but joint E will also feel a force going in its direction. So you have a force in this direction, a force in that direction. And they have to be equal because of Newton's third law of motion, okay? So yeah, if it's tension, it's tension. If it's compression, it's compression. That doesn't change. The bar, the truss can only experience one force, tension or compression, not both, okay? Any questions? I know this is, it's essentially a new topic, but how do we feel about it? Are we okay? I don't think it's hard, but on Monday I said this is easy, and suddenly students started, or on Tuesday I said this is easy, and students started laughing. No, it's not. So I personally think it's okay, right? It's bringing back concepts that we learned from chapters 3, 4, and 5, but applying them to, well, in this case, to trusses, okay? I'll let you work on your homework for this, and of course, if you don't have questions, email me. But before we finish, we still have about 25 minutes left. I do want to finish this chapter. Now, I was debating earlier with my confidant if this next topic should be on the exam. And I guess it depends on how well we cover it today. If we can finish through an example comfortably, then I may include it. If we cannot finish through an example comfortably, then we may need to finish it after the exam. But we'll see. The good thing about how this class is structured, at least for me, is that we are well ahead of the usual static schedules. So it's okay we fall behind by a week or so. It's not going to hurt us. We're still going to have enough time to cover everything. So we finished our conversations on trusses. Now we are going to talk about frames and machines. Okay? What are frames and machines? Is anybody studying mechanical or mechatronics? So don't get excited. We're not going to deal with actual machines. That's just a fancy name we give to collections of rigid bodies whose actions depend on each other. So this is one of those chapters that sounds cooler than what it is, the structural analysis. Oh my God, we're going to design structures. No, you're not. You're going to analyze trusses. Frames and machines. Oh wow, we're actually going to see machines in action. No, you're not. It's just going to be equations of equilibrium. Okay, so don't get too excited with its name. But essentially, and I'm going to try to read it from the book because I think it's much better than what I can explain. So frames, right, are used to support loads. So frames are rigid bodies that are going to support loads. Okay, so their purpose is to support loads. You can think of beams on ceilings. Okay. Have you ever seen a house like as it's being built, perhaps a wooden house or a concrete structure as well? You know that we always install the frame first, or we always build the frame first, and then we build everything else. Even in your house, you have your drywall, right? But then you also have your beams, right? Sorry?
Your studs.
Your studs, right? So what's the purpose of those? The purpose of those studs is to resist most of the weight of the house. Your house isn't supported by drywall. It's not, right? It's supported by the frames.
Holds up the house.
What?
So the wallpaper holds up the house.
It is the wallpaper that holds up the house. No, don't believe that. Okay? So that's the purpose of frames, okay? To support weights. Now machines, on the other hand, right? Machines are structures that contain moving parts. So machines are designed to transmit and alter the effects of forces. Again, sounds cooler than what it is. Like a pulley, right? So machines take a force and changes it somehow. Maybe, for example, pulleys. How do pulleys change forces? They change their direction, right? So machines are anything that's designed to alter or change a force. Yeah?
If pulleys are only meant to change the direction, then how come like when you add enough pulleys, like you can pull like a lot less than with something like very heavy?
We're going to do examples on that when we get to pulleys. So first of all, that's not one pulley, right? That's a system of pulleys, right? So here we are considering not just one change in direction, but multiple changes in direction as well as changes in components of force. So don't worry, we're going to get to that in this class. Okay? That is, I admit, one of the slightly more interesting parts of statics. Because everything else is just sum of forces equals 0 and that's it. Okay? So let's look at example. I guess 6.9 would be a good one. Again, this entire chapter is one where I don't feel too motivated to just do theory. I think it's actually better we do an example and then see how we can solve problems. Because the theory is chapters 3, 4, and 5. Okay? So let's go ahead and work with example 6.9. So in this example, we're going to deal with a frame. And the way this frame is going to be set up is it's going to be supported by 2 hinges. And call these points A, B, and C. And let's say that frame AB experiences a moment. In other words, we're applying some rotation to the frame. Okay? Now frame BC has a platform that resists a force that I'm going to call P. Now for this particular problem, we're not going to find forces. However, I do want to use it to sort of understand how these frames work or how to structure a problem with frames. First off, based on our definition of structures from Monday, how many structures do you see here? Remember, a structure is a collection of rigid bodies, right, that are connected and that interact with each other. So how many structures do you see here? Just one. How many rigid bodies do you see here? You can say 2 or 3, depending on how you want to split them up, but you can say 2 beams, or 3 if you want to include this, what do you call this? Platform or whatever. Okay? And the distinction is important. If I would have given you these 2 forces, could you have found whether these members are in tension or compression? To a certain extent. This problem will be a little bit more complicated if we want to solve it, but to a certain extent we can. But here's something to remember. Newton's third law of motion tells us that for every action there's an equal but opposite reaction. So while we have the option to study this as one structure, and perhaps we can do that to find these reaction forces, if we want to find the tensile or compressive forces in each beam, we're going to have to use one of our 2 methods, right? Joints or sections. Now, let's say that I'm looking at frame AB individually, right? So this is part of a structure, but I'm only focusing on the forces acting on this frame. First off, how many forces can you identify there right now? So if we're looking at the structure, but we only want to focus on this frame.
So 4.
Which 4?
So we have AX, AY, our tension or compression in B,
Mm-hmm.
and then our moment.
Okay. Yes, we have moment. And then we have either a tension or a compression in B. Now you can split that up into 2 components. It doesn't matter. What does matter is that the resultant of these 2 will be either a tensile force or a compressive force. Just by looking at this system, Hunter, do you think this will be tension? Do you think AB will be in tension or compression? Just by looking at the system. I don't know. I feel like this force is going to push this beam in this direction, which is actually going to compress the beam. Okay. So you have your forces on AB. Notice that we're identifying not just the reaction forces from the hinge, but we're also identifying the forces that result from the connection between AB and BC. Does that make sense? And of course the moment that we already included. Now let's look at frame BC. Leslie, which forces can you identify on frame BC?
There's the CX and CY.
Let me include the platform here too. CX and CY, sorry.
And then there's a tension BC.
Attention BC.
Yeah.
Okay. And in terms of these two forces, in which direction, if we're going to break down my forces at B into components, in which directions do you think they will act? Let's say that these 2 directions are correct.
Mm-hmm.
In which directions would these same forces act on this beam? To the left and down, like here?
No, or the opposite.
The opposite, right? So to the right
And up.
and up. Okay? So where are we getting this from? Remember, for every action, there's an equal but opposite reaction. So if we have a force Bx and By in the negative direction for both here, it's going to have to be in the positive direction for both there. Now this is going to start getting a little bit confusing, because now we're considering more, right, than just tensile or compressive forces. Okay? And of course, let's not forget our force P. Okay? This is one of the things that I feel that it's better if we look at it by working through an example. So let's see if we have an example to solve here. Looks like for frames and machines, we're only looking into pre-wire diagram. Nope, we have an example of the force. There we go. So let's look at an example where we actually look at a number so we can see how these forces actually start to relate to each other. And lo and behold, let's look at an example with multiple pulleys, just like Hunter wanted. Okay? So let's do example 614. Leslie, how do you feel about this content so far?
I feel okay about trusses. I'll have to practice it more, but yeah, there's some, we're learning it right now, so.
Riley?
I feel pretty good. This is a bit more confusing than the trusses, but.
It's okay.
I don't understand it, so.
So let's do an example, see how we feel about it later, okay? I feel like you're saying that you feel like that on purpose, so it doesn't show up on the exam. I'm on to you. I know your intentions. All right. So we're going to have a system of pulleys. Wow. You're going to want to look at your books. We have a cable connected to some hinge that is connected to this beam that is connected to this pulley. Does that make sense so far? Cable, beam, pulley. You need free rotation about the beam, okay? Or about this point in the beam. But the other side of the beam is also connected to a pulley, a larger one, a larger wheel of a pulley. We have a cable that's connected to this pulley that connects to another beam. And this beam itself is connected to a hook. Thank you. Thank you. I'll put my signature there so that you remember that I drew it. The other cable is connected to a pulley. Oh my God, that's not going to look good. Yeah, but wait, there's more. It's connected to a pulley, which itself is connected to the upper cable, which then is connected to or experiences a force of P. Yep. So that is my system of pulleys. I'm going to call these A, B, and C. And let's say that the purpose of this 3-pulley system, okay, now we're not just dealing with one pulley that just transfers tension. Now we're dealing with 3 pulleys. The purpose of this 3-pulley system is to lift up a load of 600 newtons. Okay? Now the question is, in this 3-pulley system, if I want to lift up a load of 600 newtons, what is the required force? How much force do I have to exert here to lift up 600 newtons? Can anybody give me a guess? If you're a good engineer, it will be less than 600. Are you a good engineer? Well, we'll see. All right. So let's figure that out. Okay. Is this a frame or a machine? Machine, right? Its purpose is to alter or change a force. In this case, we can obviously see how we're changing the direction of the force, but we're also changing, hopefully, the magnitude of that force. So let's see how this 3-pulley system works. Because this is a machine, it is a collection of multiple rigid bodies. Just like this frame was a collection of these 2 beams, this machine is a collection of these 3 pulleys. So, if we want to solve this system, we would probably have to take these 3 pulleys and analyze them individually. Now here's the thing. If sum of forces equals 0 for this machine, sum of forces has to equal 0 for every element in that machine, just like what we talked about sections. Okay? What that means is that if sum of forces equals 0 for this, sum of forces has to equal 0 for pulley A, it has to equal 0 for pulley B, and it has to equal 0 for pulley C. So hopefully this will allow us, right, to simplify, or not to simplify, to find our required force P a little bit easier. So let's start, okay? Let's start with pulley number A. And let's draw a free body diagram about that pulley. Let's neglect the actual weight of the pulley. So the only force that we're counteracting is not the weight, it's just the 600 Newton force. So if this is my pulley A, look at this pulley and think, what forces is this pulley experiencing?
So obviously it's being pulled down 600 newtons.
Okay. So notice that the 600 newtons is pulling on a hook that's connected to the center of the pulley. So I'll just write down my force here. What else?
It's also being held up on either side.
Okay.
And then it's being held up in the middle.
Good. Chris, do you agree? Okay.
Which pulleys is that?
A, the bottom one. So notice that we have the 600 newtons that's pulling downward, but then you have this cable pulling upward, these two cables pulling upward. But here's the thing, okay? This force, and this force, what do they all have in common from this diagram?
They're all in the same direction.
Well, they're in the same direction. What else? Like from the context of looking at this like a structure.
They're all on the same tension.
They're all on the same cable. What do we know about cables? Cables experience tension equally everywhere.
So then we divide it by 3.
Exactly, right? So we have the force along this cable has to be the same throughout the entire cable. And notice, what is that force? If we go all the way through the cable, what is that force equal to? P, right? So what we have is a force of P, P, P. So now can we solve this system using equations of statics? Okay? Sum of forces in the y direction equals 0. What are my forces in the y direction, Tyler?
Negative 600
Mm-hmm.
and positive 800. You just throw it out of the other.
Positive P. We don't know what they are. These P forces. I'll just call them P,
So
P, P equals 0.
that's not 600 for each P.
This is 600 downwards that's being pulled. But then we have a tension force P that we don't know yet. Okay? There's a force that we don't know that's being used to keep this pulley balanced. Okay? And the reason they're all the same is because notice that these forces all come from the same cable. So because they all come from the same cable, they should all have the same value. Because cables can only experience one tension.
So the hook is connected to that or the beam is connected to the pulley in the middle.
Mm-hmm.
This is, okay.
Mm-hmm.
Okay.
So sum of force in the y direction, negative 600, positive P, positive P, positive P. That gives me negative 600 plus P plus P plus P. So how much is P? There we go. Because this is 600 plus 3P. Move 600 to the other side, divide by 3, you get 200P. So we found our force of P equals 200. So look at that. We have 3 pulleys, and by connecting those pulleys, we can actually turn a force of 200 newtons into a force of 600 newtons. Go ahead.
So it's probably easier than I expected to say. But no,
Okay.
So there's not torque in the system, right? So it wouldn't matter what the radius of each pulley is, would it? Just out of curiosity. What's that?
Not for this particular problem. Because in this problem, all my forces are directed in the same direction, right? We're looking at tension. And 2, in this problem, we're not considering any rotations so far, right? Because in this problem, my forces are supposed to all balance out in terms of rotation, okay? But we will get to problems where we look at torque, just not in this section yet, okay? All right, so we found the force. It wasn't that hard, right? What if I ask you to find the force on this element? What would you do?
I know you have 2p going down.
Okay, so which of these two pulleys are you analyzing in order to find the force on this element, the tension or compression on this element?
Oh, the middle one. P.
Okay, so let's analyze pulley B. And you said that you have two P forces down?
Yeah.
What was P equal to? 200, right? And then what else do you have?
Do you still have the 600?
No, this is independent of the system.
Oh, okay.
You have 200, 200. What do you have here? You have some force holding this beam up, right? And that is the tension force. It's called T for tension. And you know it's going to be tension, right?
Oh, okay.
You know that this cannot be compression. I'll just call it T for now. So, if I want to find the tension that this element is experiencing, I can do sum of forces in the y direction. And what do I get in the y direction?
2p.
Okay? T
400.
minus 400 newtons equals 0. T just equals 400 newtons. Does that make sense so far? It's not that complicated, right? It's more of trying to figure out what's the right member to study. Finally, I would like to know what is the reaction at this hinge. Okay? I can find the reaction at this hinge by looking at the system as a whole, or I could study pulley C and figure out what this tension is. Because whatever this tension is will be what the hinge is experiencing. So if I look at pulley C, I think with this we can wrap up today's material. What time is it?
7:43.
Yeah, with this we're going to have to wrap up today's material. Riley, help me out here. What forces is pulley C experiencing?
One going up in the middle,
All right, I'll just call this a reaction force at the hinge.
and then we have a P force on the left side and the right side.
200 newtons, right?
Yeah. And,
Is that it?
and then there's one going down in the middle from our beam,
What's the magnitude of this force?
400 newtons.
400 newtons. Without even having to pull out your calculators, what's the reaction force at the hinge?
800.
That's correct. Any questions with this problem? Notice that you have to look at different free body diagrams of different elements. But once you actually get to do these diagrams, you'll notice that it's pretty much the same that we've been doing before. Now, 1 minute left. Obligatory question time. Leslie, how do you feel?
Okay.
Can you solve this problem?
Yeah.
If I were to
it's
ask you
way
this
more
problem?
complicated at the beginning than it actually is.
Yeah. Hunter?
It's all right.
Tyler? Riley? Chris? Lorenzo? Will?
Not bad.
Not bad?
This is like solved.
That's horrible. We can't do that.
I've solved that.
Yeah, this is-
I don't know about it.
I don't know, I think I would want one of these questions on the test, to be honest, like.
All right, I'll make my decision sometime this weekend. Yes, Chris?
I completely understand the math, but it's messing with my head. For that pulley, it's technically not possible, right? Like, how does the string connect also to the hook?
I'll look at it on the book. I think maybe my drawing is not very clear.
I'm pretty sure it's the same on here.
Yeah, so maybe I didn't draw it as clearly as the book did, but it is possible. Remember, it's a three-dimensional system. There's got to be some sort of...
Like, even if you took and like where it connects to
Yes,
the
it's the same
hook,
here.
if you like split it into two and like connected to each side of the pulley, then the tensions would just be halved, right?
Yep.
So if it was like a 3D model,
Yeah.
so then your tensions would be halved.
I think what Chris is trying to say is he wants us to use three-dimensional models because he wants a more realistic model.
I'm
Where
just
we
confused.
consider
It's like,
rotation.
If you pull on the string, I feel like the bottom pulley would go up because it's connected to the string itself.
Yeah,
It would. Yeah, it would.
That was just messing with my head. I don't know.
Yeah.
it
I'm
would.
sure the book should have something that says this should not move, but yeah, it would.
Okay.
So imagine that this is a fixed number. That's it.
Okay.
Okay.
Which I think in this model, we're literally just trying to figure out if I was holding that string, like
Yeah.
how much I was exerting for it not to move, right?
I think that's pretty much what it is. Yeah. So Chris, remember these are very simplified models.
Okay.
We're gonna find that it's not super realistic. It's just simplified so we can study it.